The headline screams failure. Tesla's robot project has been postponed until September, leading many to assume a technical collapse or engineering incompetence. But this delay isn't proof that the machine is broken. It is evidence of a deliberate collision with physics. The question we must ask is not whether they missed a deadline, but which physical component hit its limit first, the artificial intelligence in the brain or the mechanical muscles required to move them. The answer lies in understanding the difference between standing still and actually walking. For years, viewers have been sold on the idea that software is the hardest robotics. We assume if we can code a robot to think, it will naturally know how to act. The postponement reveals this assumption was wrong for humanoids. Achieving fluid, dynamic locomotion demands exponentially more power and torque than simply posing in static stability. While current prototypes can stand on stage or wave an arm, they cannot sustain the forces required for real-world labor without overheating or draining their batteries instantly. This delay represents a strategic pivot from demo-ready engineering to production-ready reality. In August of 2021, Elon Musk outlined a timeline promising a functional prototype within 1 year. By October 1, 2022, during the AI Day unveiling, Optimus was shown performing basic locomotion and dancing. These were impressive feats for a proof-of-concept machine weighing 481 kilograms in its digital design phase, but they highlighted significant gaps when compared to actual industrial demands. The team realized that assembling such a complex system quickly had revealed that their current actuator technology could not support sustained general-purpose work. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The specific bottleneck triggering this pause is not the AI brain hallucinating commands. It is the hardware struggling with thermal management and power density. Early concepts treated the robot as if high-level goals were enough to drive construction immediately. However, achieving human-like agility requires solving difficult problems regarding torque-to-weight ratios that current prototypes simply cannot handle under load. The delay signals that Tesla has determined their existing actuators would fail before they could perform a full shift of work. This necessitates a redesign of the electromechanical systems before further software integration can be meaningful or safe for deployment in unpredictable environments. Consider the analogy of running a marathon in flip-flops. You might take a few steps and even look like you are moving forward, but under sustained dynamic load, your feet will fail to provide the necessary grip or support. Similarly, current prototype actuators work for a single step on a controlled stage floor, but they lack the durability required when stepping onto uneven factory floors with unpredictable obstacles. Academic research confirms that generating program paths via computer-aided design simplifies offline creation for predictable environments, yet real-world unpredictability remains a formidable barrier without robust sensory feedback and actuator power density to match it. This distinction between static posing and dynamic movement is where the true engineering challenge hides. The team has shifted focus from showcasing a functional general-purpose worker capable of simple tricks to solving the electromechanical bottlenecks required for production readiness. Experts noted that while assembling such a complex machine quickly was impressive, the current hardware cannot yet support sustained labor without overheating or stalling under load. This is not a failure of vision, it is an admission that physical laws do not bend to marketing timelines. If they had launched in September with the current hardware, they would have released a robot that could pose but couldn't work for more than minutes before failing its thermal limits. The path forward now requires fixing the legs before we fix the brain. By pausing the project, Tesla avoids releasing a product with fundamental physical limits that would make it useless for its intended purpose of general-purpose labor. This sets up a narrative where future demonstrations will be slower but significantly more capable of handling real-world physics. The delay proves they are prioritizing mechanical durability over a temporary marketing win, ensuring that when the robot finally returns to the stage, it can actually do the job Musk promised rather than just looking like one on video. The statistics behind this challenge highlight the scale of the gap between simulation and reality. The initial research paper detailing high-level robot programming was 481 kilobytes in its original submission version 1, yet the physical implementation required thousands of pages of iterative testing to bridge that divide. The study involved 5 authors who spent years mapping out how computerized paths fail when faced with real-world friction and inertia. These factors explain why a timeline originally promised for completion within 1 year had to be extended as the team realized the actuator power density gap was far more significant than anticipated during early design phases. Ultimately, this postponement is the moment Tesla chose to fix the legs before fixing the brain. It separates those who want to see a robot dance from those who need it to work in a factory floor for 8 hours straight without overheating or stalling. The delay proves they are prioritizing mechanical durability over a temporary marketing win, ensuring that when the robot finally returns to the stage, it can actually do the job Musk promised rather than just looking like one on video. This is engineering precision separating hype from reality in the race for autonomous systems. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.